that this angle, the angle of refraction, is not equal to the angle of incidence. And for a situation where this velocity is faster than this velocity, the ray would actually be bent away from the perpendicular in this manner. Now, the equation which allows you to determine these two angles from the velocities is often called Snells Law in the literature, and it is simply this equation here, which relates the two angles, the angle of incidence, the angle of refraction, to the two velocities. So that allows us to determine the amount by which the ray is bent when it is transmitted through the interface. Now, for a situation where the velocity in the upper layer is lower than the velocity in the deeper layer, if the angle of incidence keeps on increasing, we eventually reach a situation where the refracted ray is bent so that it travels along the interface, as shown here. So that means that the angle of refraction has become 90 degrees. This ray of energy which travels along the interface is called a refracted ray. And that allows seismic energy to travel from a source to a receiver along a path called a refraction path, and that's illustrated here. The ray strikes the interface at such an angle that the transmitted ray refracts along the interface like this. Now, at any point along the interface on this refracted ray, energy can travel back into the upper layer and therefore back to a receiver on the surface. And if we look at a ray path traveling back into the upper layer, then it leaves the interface at this same angle at which the incident ray arrived at the interface. That angle is usually called the critical angle, in fact. So that it's possible to have a travel path for the seismic energy then from the source down to an interface such as this. Then the energy travels along the interface and back through the shallower layer to a receiver. And that is what is called a refraction path. Now, there's always some minimum distance from the source at which energy can arrive by a refraction path, and that is the distance here from the source to the point at which reflected energy would arrive back at the surface if it was incident at this critical angle. Now, if the angle of incidence of the arriving energy becomes greater than the critical angle, we have a situation where there is total reflection of the seismic energy in the layer above the interface. So we have a situation where the angle of incidence is greater than the critical angle, so that all the energy is reflected back into the upper layer and none of it is transmitted through into this lower layer. So remember then that the key point about the refraction paths is that they only occur when the velocity of the lower layer is greater than the velocity of the upper layer. And the angle, this critical angle at which refraction takes place, can be derived from Snell's law, and it turns out that it's related to the two velocities by this equation. Now, so far we've looked just at the way in which the P-wave energy was reflected from a particular interface. we've dealt only with the P wave energy. But in fact, when a ray of P wave energy strikes an interface, it actually generates some other types of wave motion, particularly the S or transverse waves. So that in fact the situation for reflection is of a P wave is actually like this, that the P wave strikes the interface, there is a reflected ray of P wave energy and a transmitted ray, but there is also a reflected ray of S wave energy and a reflected ray, a transmitted ray of S wave energy. And these are produced by what is called mode conversion, where the P wave mode energy is converted into S wave mode energy at the interface. The reflected and transmitted S wave rays leave the interface at different angles to the P wave energy, as shown here, and the equations which determine those angles once again depend on the velocities, and they're given here. We needn't worry too much about the details of those at this point. I just want to show that you can determine the angles for these particular rays from a knowledge of the velocities of the P and S waves in the two rock layers. So these then are some of the rules of reflection and refraction of energy at an interface between two different types of rocks. Now there's one other special kind of reflection energy that we need to look at that often comes into play on seismic data, and that is something called a diffraction. Now, diffraction is a particular type of reflection which takes place from a particular point on a reflector. And a common example would be like this, where we have energy leaving the source, a ray of energy traveling to a point where a reflector, that is an interface between two rocks, comes to a sudden end. Now that might happen because there is a fault in the earth, let's say, and that particular interface has been dropped down to a lower level over here at the other side of the fault, so that there is actually a sharp truncation of that reflector at the fault. And when the ray of energy strikes that end of the reflector, it doesn't reflect according to the rules that we've just outlined. It actually is scattered out in all directions from that point. So from this one incident ray we'd get rays traveling, say, to a receiver at the surface here, and also to a receiver here, and in fact to receivers at any particular point on the surface. And in a situation like this, of course, you'd also have a ray of seismic energy hitting this end of the interface, and again being scattered or diffracted in all directions from that point. Well, we've looked then at how the seismic energy is reflected from an interface, the directions at which it's reflected. Now we'll look at what proportion of that energy is reflected and what proportion is transmitted through a particular interface. This division of the energy or the amplitude of the incident wave into reflected and transmitted waves is determined by a quantity called the reflection coefficient of the particular interface. And in this case we're just looking at the reflection coefficient for P waves, since those are the waves which we normally deal with in seismic reflection work. If we have an interface separating rocks of different velocities and densities, density is usually symbolized by the Greek letter rho. So we've got a situation here where we have different velocities and different densities above and below this interface. Then imagine we have a ray of seismic energy incident at this interface with a certain amplitude, call it AI. The amplitude of the reflected ray is AR and of the transmitted ray is AT. Now the amplitude of the reflected ray is given by this equation. It's simply the amplitude of the incident ray multiplied by this quantity called the reflection coefficient. The amplitude of the transmitted ray is simply the amplitude of the incident ray multiplied by 1 minus the reflection coefficient. Now, the reflection coefficient itself is determined or depends on the velocities and densities on each side of the interface, and it's given by this equation here. You'll notice that we multiply each density by the velocity of the same material, and that product of velocity and density is called the acoustic impedance of that particular rock. So this equation for the reflection coefficient is really the difference in acoustic impedances of the two rocks divided by the sum of those acoustic impedances. Now, if we look at a particular example of reflection coefficients, a numerical example, let's suppose we had an interface separating rocks with densities of 2.1 and 2.2 grams per cubic centimeter and velocities of 2,000 and 2,300 meters per second, let's say. Then using the reflection coefficient equation, we'd find that the reflection coefficient for that interface was 0.09. So that would mean that if we had an incident ray with an amplitude of 1, then the amplitude of the reflected ray would be 0.09. So in other words, only 9% of the amplitude is reflected. If we reverse the two rocks so that we have the one with the higher velocity and higher density above the interface, then we would find that the reflection coefficient gives a negative value. Now this means that the energy reflected from the interface is reversed in polarity. That means that for the P wave, a compression part of the wave is reflected as a rarefaction. If we look at the amplitude of the transmitted rays, and remember that they were determined by a factor of 1 minus the reflection coefficient, then for the first situation here, the reflection coefficient would be 0.91, which means the amplitude of the transmitted ray is 91% of the amplitude of the incident ray. In the second case, the amplitude would be 1.09. Now at first sight it may appear that there's something wrong, that the amplitude of the reflected ray, the transmitted ray is greater than the amplitude of the incident ray. But in fact this is what happens, and it happens because the velocity of travel in this case is lower on the transmitted side of the interface than on the arrival side. The amount of energy carried by the ray cannot increase, but that amount of energy depends both on the amplitude of the wave and on its velocity of travel. And it turns out that in fact the energy in the transmitted ray is less than the energy in the incident ray, even though its amplitude has increased. Well, these then are some of the factors which govern the reflection of seismic energy from reflection interfaces in the Earth.